So now we'll bring in the calculus aspect. And the main aspect for calculus would be the derivatives. So one thing we haven't done is a derivative in parametric, things like that. Okay. But we understand now what parametrics are. All right. We get that third variable in. Typically that third variable is t, representing time. So it helps us see more about what's going on with a particular function. So the calculus aspect. The derivative dy dx equals dy dt over dx dt. Now the nice thing for us, we already know what a derivative is. We know it's y prime, f prime, whatever. We already know that the representation is dy dx. And so that'll help you remember in parametric, the y one's on top, the x is on the bottom. Okay. There's not a lot going on there. Okay? Pretty basic derivative. Right? If we go to higher order one, let's say d2y over dx2. Okay? So this would represent second derivative. This would be derivative with respect to x of dy dx over dx dt. Now it's a little bit easier than it looks. Here's what you've known from the past. If you wanted to find the second derivative, you take the derivative of the first derivative. That makes sense, right? Basic there. So if I want the second derivative, this says take the derivative of the first derivative. That's what you're used to doing. The difference is in parametric, it's always going to be divided by that original dx dt. So one difference in the parametric. Notation, remember we've seen this notation before. We don't use it an awful lot. We usually have that f double prime or y double prime, something like that. A lot of times it gets confusing. So well, wait a minute. Why is the 2 here and not here? Just remember, this is saying the second derivative. If you put the 2 in front of both these, they cancel. We don't want it to cancel. We're trying to just use a notation to tell us it's the second derivative. Something like that. Okay. So let's look at something here. Let's say find equation of tangent line to x equals t squared minus 1 and y equals t, where t equals 2. So we're going to get a little bit of a repeat of some directions we've seen before. We found equations of tangent lines a lot. We just haven't done it in parametric. So for my equation of a tangent line, I know we're in parametric here, but what's the first thing we're supposed to do every time? Do what? Say that again.
You run the rectangular.
I don't want rectangular. Point slope form. Y minus y1 equals m times x minus x1. Every time you're asked to find an equation of a line. I know that we're in parametric, but this was the instructions. So we're going to go right to that point slope form. Now, just to remind you, we wrote the point slope form down. Y minus y1 equals mx minus x1 because it told us what we needed. We need 3 things. We need an x, a y, and an m. Now I know we're in parametric form, and it might look like kind of a pain, but I've got to know what I'm looking for. The point slope form tells me that. I need a point and a slope. Well, my point. It says where t is 2. So if t is 2, what's x? 3. 2 squared minus 1. So I'm going to have y, x minus 3. 2 squared minus 1. If t is 2, what's y? 2. Not too bad. Previously, you would have just been given that xy point. Now I've just got to go find it, but I know what t is. I can find that pretty quick, no matter what I'm working with. Where do we get slope from? Derivative. Slope came from the derivative. So now's where the new piece is coming in. I'm in parametric and I want that derivative. So I'm going to take the derivative of the y divided by the derivative of the x. Okay, so dy dx would equal, what's the derivative of the y?
0.
Oh, 0. 1. All right, so derivative of t, 1. Over the x1, what would the x1 be?
2t.
2t. So there's my differential in parametric. If t equals 2, that's 1/4, right? Everybody agree with that?
Yes.
There's my slope. There's my line. The only thing really new is this derivative piece. And when you're doing the graphing of the parametrics, you were putting a t in and getting an x and a y before. So I know that's being mixed in here, but we've already seen that. We're just kind of dealing with the parametric. This idea right here is not new. But boy, we forget a lot of times. Just write down that equation. There's your point slope formula. It tells you what you need. Everybody okay there? All right. Let's change the look. Evaluate dy dx at t equals pi halves for x equals e to the t cosine t and y equals e to the t sine t. Again, our new piece is the derivative, just trying to give you, have a couple different looks at things. Now it says evaluate dy dx, that means I need the derivative. Dy dx equals, and I'm in parametric, but which one goes on top? The y one. You can always remember that because it was always the y over the x, right? This would be product rule. Doesn't matter there's a t. We've already gotten used to it. We don't care what variable's there. If that was e to the x sine x, it'd still be a product rule. Okay. So first, e to the t, derivative of the second, cosine t, plus second, sine t, derivative of the first, e to the t.
Wait, isn't the derivative of cosine negative sine? Or am I mixing that up? What's the derivative?
I did derivative of sine.
Oh, right. Yep, I have it backwards.
Alright.
Okay.
So now I go to the bottom, the x one. It's still a product rule. So first, e to the t, derivative of the second, negative sine t, plus cosine t, derivative of the first, e to the t.
Okay.
Now I've got to simplify this thing and evaluate it at t equals pi halves. So I'm going to be putting pi halves in for t, so usually I'll just write it like this. Hey, t's pi halves. But before I do that, take a look here. All the e to the t's cancel. Just one in each part.
Great.
So it gets a little bit better. So now I'm going to have cosine pi halves plus sine pi halves over negative sine pi halves plus cosine pi halves. What is the cosine of pi halves? Am I wrong? Got it? All right. So cosine of pi halves is what? 0. Those don't matter. What's the sine of pi halves?
1.
1. So that's a negative 1 on the bottom then. Just had the negative out front. Negative 1. And so our new piece is the derivative, but just getting a couple different looks here. That's how we've used derivatives before. Here's another look. Find all points of vertical and horizontal tangency to x equals t squared minus t plus 2 and y equals t cubed minus 3t. All right, horizontal and vertical tangency. That means this is where I still need that derivative. I'm talking about a tangent line, right? What's the slope of a vertical line? Undefined. What's the slope of the horizontal? 0. All right, so we're looking for where the slope, which is the derivative, is undefined, and where the derivative or the slope is 0, horizontal and vertical. Either way, I need the derivative. So, dy dx would be 3t squared minus 3, derivative of the y one, over the derivative of the x one, 2t minus 1. Everybody okay there? All right. Now, where is it vertical? Where 2t minus 1 is 0, because that would make that fraction undefined if the bottom was 0. So this would happen when t equals 1/2. Everybody okay with that? Horizontal. This will be where 3t squared minus 3 is 0, where the numerator is 0. So if the numerator was 0, the derivative would equal 0. And this would be at t equals plus or minus 1. Add your 3 over, divide by 3, square root, you get plus or minus 1. Everybody okay there? So, new piece, old ideas, just kind of reminding, it's been a while since we just worked with straight derivatives. Okay? Find all points. We found the t values. How do you find the points?
Plug those values in.
Put those values in for t. There you go. So if I put 1 in, let's see, 1 minus 1, 0 plus 2 is 2. That would be the point 2 comma negative 2. If I put negative 1 in, that'd be 1 plus 1 is 2 plus 2 is 4. And that would be negative 1 plus 3, 2. So we're finding the points the same way we did back on the graphing, right? We can put a t in, we get x and y. The half, a little more of a pain here. Let's see, that would be a fourth. Minus a half is negative fourth.
Yep.
Plus 2, 7/4. Or 1 3/4. And then on the other one, an eighth.
Minus 12/8.
Minus 12/8. So minus 3/2. And it wouldn't matter if we had decimals there or what have you, it doesn't make a difference. little more of a pain because of the fraction, but still the idea pretty basic. I got to put the t in to get the x and the y. Everybody okay there? Let's go x equals t squared minus 4 and y equals, let's go 3t plus 1. Find d2y over dx2. So what does that mean we're looking for? Second derivative. We can't find the second derivative until we do what? First derivative. So nothing new on that front. Let's see. So dy dx. 3 over 2t.
Yes.
Everybody good there? Okay. So now the derivative of that. You have a couple choices here. You can write it as a -1. You can think of it as a -1 on the t, or you can use the quotient rule. Okay. It's really entirely up to you. I usually, you've seen me most of the time, I'll make it 3/2 t to the -1. I don't really like using the quotient rule if I don't have to. Okay. So that would give you -3/2 t to the -2. So I'm looking at -3 over 2t squared over 2t. There's the difference in the parametric. So the second derivative would be the derivative of the first one. Here's my derivative of the first one, which is what this was saying back from the beginning. Divided by the dx dt again. And that dx dt was that 2t I saw before. Which is this going to be -3 over 4t cubed.
Wait, so why are you just dividing it by the 2t and why is the 3 not here?
dx dt is what we talked about.
Oh, okay, so, okay, I see.
dx dt is just the 2t. Now, what do you think you would do if you were asked to find the third derivative here?
I'm gonna say
Find
no.
the derivative of that we just found, and then put it over dt, or 2t.
You got it. And Trace would quit. He already admitted that. All right. Yeah. So if I was asked to find the third derivative, I'd find the derivative of this over 2t again. Fourth derivative, whatever I get derivative of, and then over 2t again. It's always going to be divided by that dx dt. So that is a little bit different than what we've seen. This is a little different look, but it's pretty basic. It's still the y one over the x one. Okay. All right. Next piece. You'll be fine. Arc length.
So,
Go, go.
Arc length is a to b dx dt squared plus dy dt squared square root of dt. Now, this is just our arc length formula in parametric. You know this. You can put the integrals in your calculator and solve. That's not a big deal. We've done arc length before. Here's what arc length looked like in the past, back from previous unit. This you should remember.
Kind of.
Yep. Vaguely familiar?
Yeah.
Okay, so this was we were in dy dx, right? We had the derivative, so that was that derivative there. Okay. this was actually the derivative of x, which was 1. Okay, so and put this back in terms. This would be dx squared, and this would be dy dx squared. If I didn't write it like this, but I wrote it in x's and y's. Well, that's f prime, right?
Yes.
What's dx over dx?
1.
1 squared? 1. That's why the 1 was there. Well, now we're in parametric. So this x component does matter because it might not be 1. So I'm in that parametric piece. So I'm just going to rewrite number 4 here. So let's go number 5. Arc length of x equals t squared minus 4 and y equals 3t plus 1 when t is between, I don't know, we'll go 3 and 7. We'll just do the setup here because you know you can do the integral on your calculator. This is what the setup would look like. Integral 3 to 7. I know I've got a and b out here, but remember if you have t's in here, you got a dt outside. These have got to be t limits. So I've got what I need. Square root 2t squared, the x one, x prime, plus 3 squared dt. There's my integral. And we know how to do the integrals as far as evaluating on the calculator. For my calculator, if it's something to simplify, you've heard me say this before, I will. So for me, I would make this 4t squared plus 9, just to kind of get rid of the squares. But still the same thing. Everybody okay there? So you got a new formula, but not really new. We still have an x component and a y component. That was just always 1 before. Everybody okay there? Okay. Next formula. And again, this will be done on your calculator. Surface area. You knew this was coming.
Did I?
Remember surface area had a 2 pi out front? Do you remember why?
It's 3
3-dimensional, so it's rotating it around. There we go. That's it. So we're going to have a to b, y of t, square root, dx dt squared, plus dy dt squared, dt, or s equals 2 pi, a to b, x of t. Both these up here and shut them down. We'll look at the difference between the two. Now we saw surface area in the past.
Yeah.
We saw the 2 pi, rotates it around. The a to b, I just have a and b. It doesn't matter what you have there. It's representing whatever the limits are. Okay. This part here, this was the arc length, right? So basically, we're taking the length of whatever it is we're talking about. Let's say it's right here, whatever length that is, and then we're going to rotate it around so it kind of mirrors itself, and we're going to get that full surface area, right? Everybody okay with that?
Yeah.
All right, so arc length, length of the curve, rotation, then these two guys. Y of t is in front if we're going about the x-axis. Look at this one. If I'm going about the x-axis, how far am I from the x-axis? Y units. If I were going to go this way about the y-axis, my figure would be x units from the y-axis. That's why the x of t in front.
What if you do if you're rotating? What if you do if you're rotating around the line of x equals 1?
Okay, if we're going to rotate around the line, say x equals 1, do you remember when we did, is it above or below?
Oh, yeah.
So it would be y minus 1 or 1 minus y, depending if it's above or below when we shifted it using that shell method before.
Yeah, but then.
And so, in other words, this is technically x of t minus 0, y of t minus 0. If it's shifted around, we can shift it from 0 to wherever it's shifted to. So if we were going to go about 5, x of t minus 5, y of t minus 5, or if it's to the other side, 5 minus. Okay. What we're going to see right now will be around the x and y axis, but that's where the shift would come in. We've kind of seen that before. I believe when our old surface area, you saw me just put a y or an x in front instead of an x of t or a y of t. Okay. So if I were going to do the surface area of this guy back in number 5, if I were going to go around the x-axis, I'd have the 3t minus 1 in front, or 3t plus 1. If I were going to go around the y-axis, I'd have the t squared minus 4 in front. That's the only difference there. Everybody okay there?